Hi, so welcome back. So let us finish this problem that we started talking about in the previous module. Okay, so we were going to design or look at designing a wind tunnel. Right now, let us start like this, and now we always start out by making assumptions. Okay, we do start out by making assumptions. Now, what are these assumptions? Okay, number one, the flow is steady, right, and incompressible. What does that mean? That throughout when the flow is happening throughout the wind tunnel, we can take a single value of the density. There are no drastic changes in the density as the fluid is moving into the wind tunnel, into the test section, out of the test section, through the fan, through the silencer and out, right. There is no change in that, okay. And the flow is steady. So if I were to look at the flow at a certain instance of time, I would not be seeing drastic differences in its properties. The walls are smooth. The walls are smooth. Well, the walls are smooth so that we are not going to look at any effects of the wall in this case, right. What we will be concerned about is primarily the fluid, right, I mean moves of the walls and what kind of behavior that makes. So we are not taking into account any property of the walls, okay. Although practically that is quite not possible. There will be, the walls will be undulated, walls will be rough, while walls will have small protrusions here and there, and there might be and also walls due to it might not be even clean. So you have to keep it clean as much as possible, but those are things which could play into the behavior of your fluid, right. So we are not going to do that, and we are just going to assume that the walls are smooth, okay. Disturbances and vibrations are kept at a minimum, correct. So disturbances and vibrations are kept at a minimum, right, and hence given whatever that the boundary layer is laminar. Boundary layer is laminar. So these are basically my assumptions, and the properties based on what is given to us. What we basically get is that nu is 1 point, sorry, this is 1.507 10 to the power minus 5 meters square per second, right. So this is nu, okay. Now let us go ahead and try to solve this, okay. Now first things first, let us calculate Rex, right, and that is right, okay. So that, okay, and which is equal to, okay, in this particular case, what is V? V is the incoming velocity which is given to us to be 4, right, into x. What is x? X is distance which is traveled, and what is given to us? Okay, what is given to us is that the test section of the wind tunnel is 30 centimeters diameter and 30 centimeters in length. So basically what we are saying is that this is 30 centimeters and this is 30 centimeters, this length, right. So, I have a flow which is moving from here through this, traversing the whole length and coming out of this. So, this is the entrance of the test section. Let us call this as, say, A and B. Section A is the entrance, B is the exit of the test section. So, that I am trying to find out the Reynolds number at the end of the test section. So, then x basically means it is 0.3 meters, right, and nu is as is given above. So, 1.507 10 to the power minus 5. What I get is 7.94 into 10 to the power 4, or you could usually, I would write this as, say, this is 0.0794 10 to the power 6. It is about 0.08 million. Okay. And so, we are less than 5 million. So, this is a laminar boundary layer. So, right now, so therefore, the Reynolds number at the edge of the exit of the test section, at the end of the test section, is laminar, which means that the flow is laminar, right, throughout the test section. Right, throughout the test section. Okay. Now, there is something very interesting here before I do the math. So, I am going to do this discussion a little bit. Now, what is going on here? So, now the question is that, so is it simple enough that I will have flow which comes in, right? I will have flow which comes in here, then it will go out here. What is the problem? Why do we have to? And then there is this also question here that for nearly uniform flow of 4 meters per second at the test section inlet, by how much will the center line airspeed accelerate by the end of the test section? What does that even mean? So, what is asking is that if this is 4 meters per second and nearly uniform, right. So, nearly uniform. So, basically, now if we sort of break this down, so we say have a pipe like that. This is essentially my test section, right. This is essentially my test section, and this is 30 centimeters. So, this is 0.3 meters and this dia is 0.3 meters, and what I have here is nearly so I have uniform flow which is coming in, and this is 4 meters per second, right. This is 4 meters per second. So, then the question is how will the center line, okay, how will the say I am going to call this as x, say y. Okay. So, the question is how will the central line velocity accelerate, right. What does that even mean? I mean, why are we saying that this is going to accelerate? Why are we saying that in the central line is going to accelerate? Okay. Now, let us look at this. Okay. Before we start even doing this, let us look at this. Now, you would have the same case. So, if you have flow, I am going to exaggerate this a little bit, right. So, these are basically the walls. Okay. These are the walls of the in this case our test section or pipe or whatever it is, right. And you have a free stream which comes in, right. You have a uniform free stream which comes in. So, in the normal case what will happen is you will have free streams which will just continue to go, which will continue to go. But however, that is not that's not what we seem to be, it doesn't seem to be happening. Now, what is the case here? Now, what is happening here is that what we will have is that there will be a development of a boundary layer, there will be a development of a boundary layer, right, on both sides. And let me call that, so say here at some location, right. Now, this height is basically nothing but delta. Similarly, this height is nothing but delta. Now, because of the existence of this boundary layer, right, now a streamline, like we had discussed in a couple of models back. So, this streamline, when it encounters here, right, that this streamline, when it comes here, it is going to be pushed away from the wall because of the existence of the boundary layer, right. Similarly, at the lower wall, so if it comes here, it is going to be shifted away from itself, from the lower wall, because of the existence of the boundary layer. So, in that case, okay, let me just okay. So, okay. So, therefore, I will have, so I have a streamline, right, from say at this particular point, right. So, I could actually draw another thing like that, and I could draw another sort of thing like that, such that if I were to move, right, at any location. So, for example, at this location, right, what will happen is at this location again, right. So, this is the part, and this is nothing but the displacement thickness, right. This is the distance by which the streamline is going to be displaced away from the boundary layer, right. Now, this is a flow picture where this is actually supposed to be the core area. This is actually called the core, right. Now, flow is moving like this, okay. And so, you have flow which is basically moving like this, and this is the region where shear stress is not 0, okay, is existent, and this is shear stress is 0. So, this here is the inviscid or irrotational flow, right, but this is the boundary layer. So, viscous effects are dominating in this region, right. So, now, let us understand this just a little bit more. So, again, if I were to draw this, right. So, now here I have this is my wall, okay. This is my wall, and these are the two walls of my test section here, right. And let me also then do this. So, then this, okay. So, then what this distance is all about, this is nothing but delta plus delta star, okay. Similarly, this is delta plus delta star, right. Now, what I am going to do now is basically, so in our case, right, this is the diameter. So, let us say that this height, okay, this height is say h naught, okay. So, this height is nothing but which is h naught. Now, if I were to draw a velocity profile right here at the entrance, so say at this point, okay. Now, if I do this, okay, let us draw a velocity profile right at the entrance, somewhere here, okay. So, if I do this, okay. So, I am going to draw that. So, this is my velocity profile. at say this location, right, at this location. Now, and say this location is say location say x is equal to say x1. Okay. Now, let us come to another location which is say x is equal to x2. Now, the question is, how will the velocity profile look like? And I think I had posed this question in a couple of models back, is that say this velocity here, okay, let the value of this be say u naught, right. What happens if I move along x, right? If I move along x like that, then what happens to this u naught? Does it increase or does it decrease? Now, if you look here, right, now the total mass flow, right, at the section x is equal to x1 is what? Okay. So, let me call that as say m1, right, and that is going to be say u naught, right, h naught, right, into okay, now that's okay. So, u naught, h naught, okay, into b, right, which is just a the breadth. Okay. So, this is the mass flow. This is the total mass flow through x1. Right. Now, we clearly know that the velocity here, through this is going to be something like this, right, and the velocity from here to here is also going to be something like this, right, because of the existence of the boundary layer. That means that say this is the delta here. So, the corresponding height here, we are not going to be able to keep the velocity at u naught. This velocity is going to be less than u naught, isn't it? So, for example, it is u naught at the wall right here, but it is 0 here, right, at x2. So, similarly, here it is u naught, okay, it is u naught here, but this thing is less than u naught. So, however, if I have to apply mass conservation at these two sections, right, the total mass flowing at section x1 through this height h naught should be the same at x1 as well as x2. So, which means right, that m2 should be equal to velocity h naught b, right. Now, if that has to happen, we know that near the walls the velocity is less than u naught, right, less than u naught, and it's only become u naught away from the walls at distance delta plus delta star from whatever I can see here. In that case, therefore, right, this velocity, right, this velocity has to increase, right, this velocity has to be more than u naught to compensate for the whole thing, right. So that when I have this, so therefore my mass is conserved, which means that here, so here say the velocity is say u2, right. So, basically what I am saying is that u2 is larger than u naught, okay, and within this, within the displaced within the boundary layer thickness and displaced thickness here. So, here basically say if I say say if I take say u1 and if I take this as u2, so both u1 and u2 is less than u naught, right. I think that makes sense. So, therefore, this question that how does the central line velocity accelerate, or what is the acceleration? So, the first question is why will it accelerate in the first place? So, this is the reason. So, therefore, what is happening is you could also look at here another way of looking at this displacement thickness, that it is almost like, it is the displacement thickness is almost like an extra thickness of the wall itself, right. So that is almost like behaving like another layer, right, a thick wall. So that the path, the free path available for the flow to move is decreased, right, but it has to keep the same mass, which is moving through the two sections. Therefore, it will need to accelerate so that law of mass conservation is valid. So, hence in this core region, so therefore, in this core region flow is basically accelerating. So, that is what we mean, right. So, now going back to the problem. So, then delta star this we have done earlier, right. So, at the end of the boundary layer, so here basically you can take delta star is 1.72 and x is the end of the test section, and this is something that we have calculated, which is 7.94 10 to the power 4, and what I get is 1.83 millimeters. Okay. Now, what we will do is look at this here, right, when we are here. So, what we will do is we will look at the cross sectional view of both these, the inlet as well as the the entrance as well as the end of the test section. Why? Right. So, if I were to look at this, for example, right. So, for example, if I let me just go back here. So, this is the right. So, this is nothing but the radius, and this is given to be 15 centimeters, the diameter is 30 centimeters. So, this is the entrance. To the test section. Okay. And now, what happens? This is the end. This is the end of the test section. Now, like I said, this displacement thickness, boundary layer displacement thickness here, right. Now, this actually behaves, like as if there is, there is an extra thickness to the wall, right. So, that it will be displaced from there, right. So, the end of the test section therefore, so if I were to exaggerate that, so the flow is going to be displaced, right, from the wall, right, from this wall is going to be displaced, right, by how much? By delta. So, this distance is nothing but, delta star, right. So, that this is nothing but r minus delta star, right. So, this is nothing but delta star. So, then now, however, right from the entrance to the end, right, the conservation of mass has to be valid, right. So, therefore, I can we'll write the very simple equation. So, this is section A and this is section B, right. So, now VB area B, okay. This is basically velocity, okay, and it's the same fluid. So, rho is same. So, you just have to multiply rho. So, I am cancelling that out, is equal to VA area A, right. So, then basically we need to calculate VB, right, which is equal to VA area A by area B. Now, VA is 4, which is given to us, right. Achha. Area A, what is area A? It is pi r square, and area B is pi r minus delta square, right. So, using this, what I get as VB is essentially 4.1 meter per second. What I get is 4.1 meter per second. Okay. So, delta star is this value. Okay. So, I get that. So, essentially what I see here is that the airspeed increases approximately by 2.5%, right. The airspeed increases by 2.1% for the test section due to the effect of the delta star, right. So, it does increase by that. Okay. Now, the other question was that what would be a good way to design the wind tunnel, so that we get more or less uniform test section flow, right. Now, this is basically just for your knowledge. Okay. So, the kind of things one would do, right, is, okay, sorry, let us go back here. Right. So, what we understand here, right, what we see, so what in this particular case, so the way we have here, we have a diffuser, right, and then this wall straightens out, the wall straightens out, right. But what we have seen is that because of the boundary layer, the displacement thickness, it is almost acting like, a thickness of the wall, right. So, in that case, so that because of that, it is going to not give you this entire area for the flow to move. So, instead of keeping this horizontal like that, so you could diverge it, you could diverge it, right. So, that I get a little more space for the flow to move. So, that is one of the things one can do. Another thing is that you can use, right, a suction pump, okay, and suck out all this air, which is sitting on the walls here, and creating a boundary layer which is displacing the air which comes here into here, which comes near the walls away from it. Okay. So, that is also a possibility. Now, that is something is also expensive. So, one will have to be careful. Okay, I think we will stop here. I wanted to do another example because I thought that would be interesting, but hopefully we can another time. So, for now I think we will stop and take this up again in the next module. So, thank you.